All right, hello and welcome everyone to Celestial Theodolite update number 19. Tonight, the agenda is going to be Mike going over a PDF that he wanted to touch on, and then I'm going to go over a presentation regarding celestial and terrestrial refraction, and we're going to have an in-depth analysis, peak by peak, star by star in some cases, of the amount of astronomical refraction and terrestrial refraction present. We're going to analyze one of the arguments that's been put forward, that is that the celestial theodolite can be done with a more simple explanation by combining terrestrial and celestial refraction, and we'll see how that plays out as we go through the measurements in our analysis. So to kick us off, the format, of course, will be for Mike's presentation. If you could please hold your questions until the end, that would be awesome. When I'm giving my presentation, if use your best judgment if you think it's pertinent to ask a question during the middle of that. If not, you just wait till it's over. But everyone's pretty cordial here for the most part, so we should be good to go. Mike, whenever you're ready, good sir.
Okay, I'll go ahead and
I'm sorry. I'm sorry. Real quick, the moderators for this evening will be Galatrax and Biasticles. If you have any questions that you have about the celestial theodolite, you would like to ask them, or maybe you don't want to ask in public because you have some, anxiety or something, you can send them a DM and they will forward their message. We will go over all the questions at the end of the night. All right. Sorry. Go ahead and continue, Mike.
No problem. I posted this to the live stream text, so anyone who's interested and can find a hard copy of the PDF there. And basically, this summarizes our findings. And there's a new tautology here. This is a hard, fast rule that the globe angle equals the flat Earth angle minus the distance angle. And the distance angle is defined later on as the distance times 360 degrees over 2 pi r. So it's just the distance expressed as an angle. And another important angle is the apparent angle. This is the one we have been talking about extensively for it seems like months now. Maybe it's not that long, but um, uh, this is basically the globe angle plus refraction. And what I'm pointing out here is what our globe Earth friends are calling refraction is really just half the distance angle. Um, and refraction is extremely important to our globe friends because without refraction, they can't explain the many anomalies their theory experiences near the horizon.
Real quick, Mike, you're
Um,
speaking of astronomic refraction, correct? Not terrestrial.
I I am, and sorry I didn't clarify that. So um, when I'm talking about if whenever I'm talking about refraction, I'm talking about celestial refraction. And
Hi, Mike and
um,
John.
the the celestial refraction is really just half the distance angle. No matter how they try to dress it up, that's all it is. So it's because of all our talk about the celestial refraction. Um, I dug deeper and deeper and deeper to figure out what's going on. Um, at John's suggestion, I included temperature and pressure data, and that made things great for Pikes Peak, but it actually made it worse everywhere else. And so I was digging some more, and but in the end, um, there is absolutely zero doubt that perfect refraction is actually one half the distance angle always. In fact, I highlighted that right here. Um, if you have something, if you've got your pressure and temperature and every other factor you want to dialed in perfectly, so that the angle is spot on and agrees with a properly corrected terrestrial theodolite, um, so that they match perfectly. The amount of celestial refraction you have is exactly 1/2 the distance angle. So this is the scam that our globe Earth friends are pulling. And I actually give an example using numbers from my house, and these are the actual numbers. Um, and so basically, what this paper is doing is this is saying because of these angles and what they show, the globe Earth myth is dead. Um, it doesn't even have a heartbeat anymore. It's all just talk from this point on.
Not even a
And
defibrillator is going to help it. Yeah.
right, not even a defibrillator is going to help it. You can't bring it back because these these equations tell you exactly what is creating the illusion. And so if there's any questions before I turn it back over to Alan, I'll be happy to answer them.
So yeah, I got a question about the 360 times the distance. So we know that 360 times the distance gives us the globe drop amount, and then or to the star rather for like the for the full position where that is, and then half of that's 180 times the distance gives us what they would predict for the physical elevation of a mountain peak, for example, relative to that distance, and the refraction amount at the astronomical refraction amount that they apply low at the horizon like that is basically 1 to 1 whatever the uh, other half of the 180 of the drop would be to make the full 360. Is that what you're saying?
So I'm saying when you add 1/2 of the distance to the uncorrected angle, which is called theta sub g, and that's the raw uncorrected globe Earth angle from the observer's location, looking at where stellarium says the star really is, not where it's refracted to. If to that angle you add 1/2 the distance angle, that brings you up to perfectly refraction corrected, what they call the apparent angle. And that's the one that terrestrial theodolites measure. That's the one we've actually been talking about all these weeks. Every time we're talking about the angle, we're actually like in Pike's Peak case, that's the one that would be 2 degrees 17 arc minutes if it were perfectly corrected. So perfect correction is 2 degrees, 16 arc minutes, 56.2 arc seconds, and that's a misprint. It put arc minutes again there, but that's that's the perfect angle. And 218, 219, 222, any other numbers they come up with, that's imperfectly corrected, and that doesn't really point to the peak. But 2 degrees, 16 minutes, and 56.2 seconds points precisely to the top of the peak, and that is exactly 1/2 the distance angle.
Oh, dang. So that's a whole so the half the distance angle thing is a whole new layer to it then.
Yeah, actually, that's the same thing. Well, all right, I was going to say it's the same thing you discovered, but you and I had some
It's
coincidental discoveries using different means, and I don't want to steal any of your thunder, so you can talk about that. But if there are any more questions about this, I'll be happy to answer them.
awesome. There do not appear to be any questions regarding that. All right.
All right then.
So let me see if I can. Screen share is not going to work. Let me download. Uno momento. All right, here we go. All right, 1 second here. Let me send this PDF out to the boys so everybody can get a copy. So view update 19. All right, gentlemen, here we go. So to give us a little recap of astronomical and celestial refraction, we need to understand the difference between terrestrial and celestial refraction mechanistically to understand their differences and how they're not related and why it's inappropriate to relate the two together or to try and combine them. So here we have a simple example of Snell's law. We have the drain here at the bottom of the sink. When there's no medium in between you and the sink, you can't see it. When you fill the sink with water, you can see the drain. It has a lifting effect. Now, terrestrial refraction has assuming a uniform lapse rate, will lift objects proportionally vertically to create this effect. And astronomical refraction doesn't have that same vertical proportionality ratio. It does act as a magnifying effect, which does cause the lift, but it doesn't do it in the same way that causes the vertical proportionality that preserves the form of the object and the ability to lift it over. So what we're going to look at here, or as it lifts over an object. So what we're looking at here is a side diagram of the drain, the light coming from the drain, and then it's being bent when it hits the water here to your eye. So that's what's lit. That's what's causing the change in the light path there to represent that. Now, if you flip that upside down, we would the inverse of that would be, or the reverse of that would be the light coming from the sky and how refraction would make it bend up. Okay. All right, so little diagram here. Now, the diagrams that we're going to go over obviously aren't going to be to scale, but to give the best representation here, I pulled a couple of diagrams from some textbooks to show the what we're talking about here in regards to where the real position of a star is versus the apparent position, which is the refracted position. And that's dictated by the amount of astronomical refraction, not to be confused with terrestrial, even when it's close to the horizon. And we'll get into the reasons why further as we go on through the PDF here. But again, apparent position, you see it's lifted up, it appears higher. Real position's lower. And that's what we're looking at here. So when light slows down, entering the dense atmosphere, it bends down towards the surface, causing the sights to appear higher. Very cool. Another citation here, just showing the same effect with a slightly better diagram, but same exact premise. Source is below, apparent position is lifted higher. All right. So for celestial refraction for angles that are not at the horizon, you can use a simple formula of refraction equals 57 over the tangent of the angle, and that will give you approximately however much refraction there is per the angles that are above 20 degrees above the horizon. When you get to 20 degrees and below, you have to start using specialized formulae. The primary one that is often cited is by G.G. Bennett, and that's noted here by the cotangent function and a couple of coefficients that are applied to the angle as a multiplier. So instead of having the angle diverge to 0, it increases it. So this is what is basically, if you can think of the tangent function, showing how the star converges to 0, the opposite would be we need a lifting function as it converges to 0. So this 10.3 and the 5.11 here are just offsets to the angle that you apply. They have nothing to do with the amount of actual refraction in the area. And we'll get into some theory on how they model out the calculations for the models to produce these numbers, and it's based off of Stokes' theorem for air mass density being exactly proportional to the density at the horizon, so that it creates a uniform gradient, so that they could say, hey, there must be this much refraction, because if there's not, then we don't have the ability to explain why the star isn't following the 15 degrees per hour and then being occluded by the Earth when it gets low at the horizon. We need to explain why it's lingering. So these coefficients here apply to real world observations, curve fit to make the correction fit what it needs to be to maintain usefulness to the model, not necessarily that these numbers have anything to do with how much refraction there is. Now, there is an adjustment here that you can add for temperature and pressure, but the driving force of the formula is actually these bad boys right here. All right. Okay, so as we get into the analysis, what we discovered with the occlusion timings and analyzing the difference in position with respect to the true position of the star and the peak, which causes the actual occlusion, versus looking at it from the observer position, we're able, and how much refraction is prescribed by the formulae provided by G.G. Bennett. And we could see how much refraction there actually was, and we could come up with we can actually take that amount of refraction and turn it into a distance. So instead of thinking of it in terms of an angle, we can think of it as lift and drop in terms of meters, which helps just really easy to contextualize what's happening. So as we get into that part of the analysis, we're going to go over a couple of things to understand the diagrams because they're written in notation. So we're going to do a quick overview of what the notations are supposed to represent, and then we'll get into the figures once we see the diagrams. So this is just a quick recap of what's going on. At a star's zenith position, there's little refraction. Probably, the most you'll get is 2 to 3 arc minutes of refraction, or I'm sorry, arc seconds of refraction at your zenith. And then as you get, an angle off of that zenith, you're going to get anywhere from arc seconds to arc minutes, a couple of arc minutes. And then as you get lower to the horizon, the arc minutes become, instead of getting 2 or 4 or 6 arc minutes, it becomes 26, 28, the really high numbers, 16, 17, 18, it gets up there. And that comes out of those, that formula we went over to apply how much that angle needs to increase by. Okay. So if you input an angle of say 2 degrees, 16, I'm sorry, say you put in an angle of 2 degrees, 6 arc minutes, this is going to tell you need to add 11 arc minutes or 12 arc minutes to it to lift it up. So that's the impact of what they're doing there. So that's what that represents. The notation, of course, is pretty straightforward. It's just H observer, H peak, delta H was the difference in their two heights to create the relative mountain altitude, which will have different physical elevations depending on if the prediction is for a flat Earth or a globe Earth, because the globe Earth would predict physical geometric drop over distance, which dictates that the elevation is physically lower because of that, which corresponds to their angular measurement. So if those two don't match, then there's no drop over distance. So geopeak here is representing the rise over run of the distance in the observer height difference to the peak. So that, or the elevation difference, sorry. So that gives you the rise over run to the peak. So that gives you the angle to the peak. The peak geo drop gives you the 180 times the distance over 2 pi r, which is the raw globe, the geometric globe angle for what the elevation would be, accounting for that missing drop. So this will output an angle amount. You subtract that from the geopeak amount, and that will tell you the elevation of the mountain for the globe prediction. Let's see, there's globe peak apparent, which is adding standard refraction to the peak drop, which will be useful for the analysis when we go over John's diagram. We have the star observer apparent, which represents the star's position with refraction applied. The true position for the observer, so that's the star's position with no refraction with respect to the observer. And we have the same for the peak with respect to apparent and true positions at the peak location. And we have the star, we have the star geometric observation prediction. So that's just predicting where the star would be using 360 times the distance over 2 pi r to get the full drop to the star. So we'll see how that plays out as well. And we have refraction astronomical Bennett, which is the formula that dictates how much refraction there's going to be at the horizon. This appears to be what stellarium is using. This gives the same values that stellarium gives at the horizon. So they match there. So refraction astronomical measured. This is the measured astronomical refraction based off of the difference between the true position of the star at the peak and the true elevation of the peak. And so that angular amount will give us how much refraction there actually was. And that'll be super important as we continue on. And then we have refraction astra over compensation. We're going to subtract the amount of measured refraction from the amount of prescribed refraction from the formula. And we're going to look at that difference. And we're also going to convert that into meters and see how much the overcompensation amount affected the measurement in terms of your compensation for drop over distance. So tangents, these are just explaining the math functions. So just functions of a triangle, and converting distances based off of a central angle to a sphere with a radius of r. So that's where the 180 times the distance comes from. And then the 360 times the distance over 2 pi r. That's where all that's in relation to. All right, and the true geometric position, of course, is the position of the star with respect to the first point of Aries, which is the ground position of where the star once was on the vernal equinox. You can use your favorite astronomy software to reference that angle by referencing the occlusion time and turning atmospheric conditions off. And that will tell you where the star is when adding 15 degrees per hour to where it once was to match your local time. And that will give you that location. Okay. So now we're going to get into John's argument. Okay, so John's argument primarily rests on the fact that refraction is going to have to lift up the object 1-to-1 over the object that's physically occluding it. So we'll go over the diagram here, and then I will go over the steelman of his argument, and hopefully John's there. He can give me a nod, yes or no, if he approves of my steelman.
Yeah, I'm listening.
Fantastic. Okay, so we have so arguably he would say that it is easier to determine the occlusion timing because all you have to do is go to the observer location rather than the peak location, enter the relative globe angle for the peak at that time, which accounts for drop over distance. When you do that, the peak with astronomical refraction will be aligned with the peak at that same time. Is that kind of basically it?
Yeah, clearly the picture shows the star and the peak right next to each other, right? At the occlusion time.
Fantastic. All right, in this place that the physical occlusion happens, and that's something that we all agree on. So that's an awesome foundational premise for us to build upon. So here we have the relative angles here. We got 219 for the raw globe angle, giving that and it intersects with the apparent position for the observer. And then we...
Quick correction.
Yes.
I mean, that 219 is tangent to the ray that comes from the star and passes over the peak. Just before it's occluded, it's passing over the peak, continuing to curve so that when it enters Mike Heffron's eye, it's coming down at an angle of 2 degrees 19 arc minutes, as Stellarium says.
Absolutely. All right. So now we've got all that established here, and we can see here's the familiar 27, and we can get that from 360 times the distance over 2 pi r. So same relationship. There's different ways to get to these values here, but the important factor is that we're all representing the same thing, right? No one's saying that the star is somewhere where it shouldn't be. So we're all good there. So to better understand John's argument, we need to break his diagram into two sections: terrestrial and celestial predictions, respectively, because it's the geometric intersections of these two that creates the occlusion for the observer at x distance away. So, beginning part, terrestrial. The argument made by John is that by referencing the star at the observer location with refraction, the occlusion is predicted at the angle of 219. That angle closely aligns with the geometric globe apparent peak angle, which is, after accounting for terrestrial refraction, comes to 219 because the raw angle is 217. As noted in the diagram, the place that the physical occlusion happens is something I completely agree with, and that's extremely important to understand as we continue the analysis. The second part of John's argument is the celestial. From the observer's location at the time of occlusion, the geometric location of the star is given by 360 times the distance over 2 pi r, producing an angle of 2 degrees and 6 arc minutes, to which refraction astronomical Bennett is applied, making the new angle 2 degrees and 19 minutes at the observer location. So if the terrestrial angle equals 219 and the celestial angle equals 219, it logically follows that the physical intersection occurred close to 217 and is viewed by the observer at 219 due to astronomical and terrestrial refraction. Conditions only possible if the Earth's were a sphere. John's primary argument is that this method of occlusion prediction is simpler because you can use the observer location. While in most cases this method is only off by a few arc minutes, it cannot truly tell us if the elevation of the peak was occluded by the star without assuming its correctness and looking no further. But as we are on a quest for truth, we will look further. So, John, real quick before we continue on, so far, everything I said, pretty much, I'm not straw manning you.
Yeah, no, I'm impressed. It's very good.
Thank you, sir. Fantastic. All right. So, step 3, putting it all together. A globular proponent would argue that this is no coincidence, asserting that those angles match because the Earth is a sphere. Predicted the physical elevation with refraction matches the apparent position of the star at the time of occlusion. Logically follows that if the star's true position is sub 11 arc minutes below the apparent peak, it is being refracted above the peak 1-to-1. Once the entire 12 arc minutes of the peak is eaten up, the star is visually occluded for an observer 50,700 meters away. Therefore, the Earth must truly be a sphere. John, one more time. Let me hear you. Can I get an amen, brother?
I think so. I need to look at that a little more, but I think what you're saying there sounds right.
Awesome.
That's
Awesome.
right. And I just note the one thing is that the nice thing about my diagram is that it shows that the geometric direction to the star from both the peak and Heffron's place is the same as it must be.
Indubitably. All right, so we went over the refraction and bending of the light already. So here's just a quick recap on that. Source is lower, apparent position's higher. All right. An immediate contention I have with John's diagram is that 219 is being the reference for the elevation for all this to transpire on a globe. The refracted 2 arc minutes lifted to the peak does not physically occlude the star as something that is refracted as a non-physical and has no ability to cause the occlusion. Therefore, the standard atmospheric correction is not considered when analyzing the physical intersection of celestial bodies with the terrestrial. That choice will be later quantified in the differences in the angular separation between the geometric peak and the star's true position with respect to the peak. And it will be shown that the terrestrial refraction amount at the observer's location has no impact on the measurement. Because the true position of 2.6 is given to match the 219 by way of astronomical refraction, lifting it to 217 and then allowing for terrestrial to make up the last 2 difference there for 219. There's only 12 arc minutes of refraction and the star is already at 217. Lifting the star another 2 arc minutes to the optical globe prediction for the globe geometric peak is improper. Citations from Andrew Young will apply here, and we'll go over those here in a minute. When we analyze Mount Rosa, it will be shown that the standard refraction has no meaningful impact on the occlusions. We have an occlusion separation difference in the arc seconds, and the terrestrial refraction is 2 arc minutes there. So if it was present in these measurements, it would affect that, but we'll cover that in more detail as we continue. A quick recap of Young reminds us that terrestrial and astronomical refraction, while having the same effect, are mechanistically different, leading to a different magnitude in the effect. The terrestrial path that light experiences is a constant angular displacement for all vertical parts because of the constant lapse rate. The path of light is affected by the temperature and pressure changes near eye level or below. This creates a proportional vertical lift, allowing an object to maintain its form and visibility when it would otherwise be occluded. On the other hand, astronomical refraction near the horizon is said to follow Laplace's theorem. Sorry, I said Stokes' theorem earlier. I meant Laplace's, which is a proportionality ratio to air mass, and that the line of sight angle to an object, which is equivalent to assuming a static uniform condition in order to describe a universal amount of refraction to apply to observations near the horizon that don't follow 15 degrees per hour. And this weakness of assumption is even noted by Andrew Young himself. So this is the foundational premise, the axiom to which all calculations and models of celestial refraction are built upon, so that Bennett, so that the GG Bennett guy could empirically derive those coefficients to fit the actual observations. And using Laplace's theorem of air density is how they build the computational model to outwardly project the uniform spherical gradient of atmosphere that is required to bend the light in such a way that it maintains that 15 degree per hour usefulness, just perfectly compensating. Light from celestial bodies passes through the entire atmosphere without interacting with the boundary layer of the atmosphere. And that boundary layer is that atmosphere close to the surface where the temperature effects are the greatest and it is most impacted. So when we look at measurements throughout the day, like this famous Skunks Bay varying throughout the day, all of those conditions are, within the boundary layer. It's the most affected by it. And that's why you're going to see that vertical lift. But as you get further away from that boundary layer, it's basically physically disconnected from the layers above that, which would be where the astronomical refraction comes into play due to the path of light coming from above. So it actually doesn't interact with any of the temperature or pressure changes that are occurring in the boundary layer. So the air above that layer is virtually, someone's mic is hot micing, please. Thank you. The air above that layer is virtually unconnected and therefore has no influence to the boundary layer conditions. Because there is no terrestrial influence, there is no way to infer the thermal conditions along the path of light to the celestial body, or from a celestial body. And that's a quote from Andrew Young. The weakness of Laplace's theorem of atmospheric density, that part was the quote, and the rest of it was kind of paraphrased. But anyway, the weakness of Laplace's theorem of atmospheric density air mass proportionality is that in order to maintain the 15 degrees per hour inherent to the 60 nautical miles per degree relationship, empirically derived astronomical corrections will end up curve fitting what the conditions have to be to maintain the two-sphere model, rather than modeling actual conditions independent of the model that it's trying to compensate for. And then that's an error there. In lieu of terrestrial refraction playing no part in celestial terrestrial occlusions, the globularist hypothesis that the optical occlusion is already untenable. We can see instances where, in order to explain the measurement, the occlusion would have to occur inside of the refracted image of the peak, delaying the occlusion until the apparent star position was lower than the geometric peak drop. Because the occlusion time is the physical, because the occlusion time of the physical intersection is only one time, we don't have to consider it happening at a different time. So we're free to dismiss that. But we're going to continue on. And I kind of wrote this very negatively because I was like 2 a.m. or whatever when I started writing this. But we're going to see it through and not dismiss it. But on the premise of it, it's already lower than what is allowed. But we're going to continue anyway to see it through, to see what it would play out, granting the as if we didn't know beforehand or whatever. Okay, so I wrote this before, after knowing. But anyway, nevertheless, we'll continue analyzing and granting them the close enough for the purposes of analyzing the dynamic astronomical refraction conditions to the empirically derived curve fit static model. To find out if John's hypothesis about the hybrid of terrestrial and astronomical refraction lifting the celestial bodies 1-to-1 over terrestrial objects is correct, the star, would have to be lifted up by 12 arc minutes to cause to cause that peak to intersect at 217, which optically gets refracted up to 219. We would need to reference the peak's true position we would need to reference the star's true position at the peak at the time of occlusion for the observer, who is 50,000.7 meters away. The distance, the position of the star is given by the true position with respect to the peak, and that should intersect with the geometric peak or the geometric globe peak, which will tell us the angular separation between the light source and the true position of the peak at the time, whether it be globe angle or flat Earth angle. To test John's hypothesis, the hybrid terrestrial astronomical of whether or not it refracts 1-to-1 over the objects being lifted, we must check. Did I just type that out twice? Sure did. We must check whether this produces the effect predicted at the intersection at the top of the peak. Specifically, when the peak is at 217, it is said to be optically refracted to 219. To verify this, we need to observe it. I did type it twice. Okay, my bad. Because Okay. Remembering that the star is also lifted up 12 arc minutes relative to the peak, the star must linger, looming above the peak until the star is occluded at 206. This would create an angular condition. This would create the correct angular conditions on one hand, but it would demand that there would be a physically different occlusion timing. And if you wait until the star is at 206 with respect to the peak, the occlusion timing would be 2:18:45:35, which wasn't observed, a time which wasn't observed at the occlusion. So we can render that untenable and consider it no further. So we're only considering the intersection angle at the peak. We're not waiting for it to line up, because it's not occluding then. It's occluding when the intersection is only like 2 to 4 arc minutes. We'll go over the scenarios there, but the premise is they should have to match if the refraction lift is 1-to-1, which would create effects where stars get occluded by mountain peaks, but they're just lingering there for a little bit because the refraction difference has to be fully compensated by the star dropping enough below it angularly so that it actually gets occluded. So when, but that's not what's observed. We see the star disappear pretty much immediately, and then we can reference where it was with the peak to determine how much further below the peak it had to get, so to speak, before it was actually occluded for the observer. So we simply want to know which angle the true position of the star is at, and if it's closer to the globe peak or the geometric peak predicted with no drop. That will tell us the relative physical elevation of the peak based on our distance away from it, which is directly linked to the geometry of Earth. The angular separation between the peak of the star will give us an idea of how much actual refraction there was. Here we introduce several new metrics so that we can go over the comparison for the refraction analysis and determine what constitutes as a valid measurement. So here we have the variables introduced are astrorefraction Bennett, astrorefraction measured, and astrorefraction overcompensation. The first two are straightforward enough, by using a tangent function, we can convert the amounts based on the relative distance into meters, and we can think of it as lift and drop to see how these things are affecting the measurements relative to the elevation of the peak in meters instead of angles. Essentially, the same process. I just went over that. All right. Oh yeah. So we can do that same process to convert the. Actually, I just said that. So finally, by taking the difference between the two, we get astrorefraction overcompensation. So by taking the difference of the prescribed amount versus how much was measured at the time of occlusion with respect to the peak, we can convert that into meters and compare that exact amount and go from there. So this will provide a useful tool for us to analyze how much curvature is being offset by astronomical refraction, and this will enable us to make a definitive distinction between Earth curvature and refraction. Okay. So to start us off here, we're going to go with Pike's Peak. So the globe, go over the stats here. Geometrically, we have 2 degrees 31 arc minutes, and then we subtract 13.5 arc minutes from that, which gives us 217 for the geometric peak. If you account for terrestrial refraction, that would give you 219 there. The star's apparent position at the time of occlusion for the observer was 219. The predicted location for the star, given by 360 times the distance over 2 pi r, is 27 arc minutes, subtracted from the true elevation of the angle that we derived earlier, and that gives us 2 degrees 6 arc minutes. The star was observed, the star's position with respect to the observers, the true position was 2 degrees 6 arc minutes. The astronomical refraction at Pike's Peak was said to be 13 arc minutes for the observer and also for an observer if they were on the peak. So in Stellarium, it'll tell you the same amount, even though there's an elevation increase there, same amount of refraction. All right. Now, for the flat Earth prediction, we have the 231 to the peak because there's no drop over distance. We have 233 at the time of occlusion, so that's where the true position of the star was at the time of occlusion for the peak. Here we have the apparent position of the star at the peak, which is given by 245. So that's adding the 13 amount, or the 13 arc minutes of refraction. Someone's microphone's a little hot there. If someone could take, oh, it's Coco. Coco, you're hot micing. Thank you, sir, or thank you, ma'am. All right. Let's see. Where were we at here? Sorry, that threw me off a little bit. Okay, so we've got their refraction here at the peak, so it gives us 245. Now the measured difference here is -2 because the refraction actually made us exceed the peak there. We'll get to that in the analysis here. We'll see what that looks like. And the amount of overcompensation here is when you add -2 to 13, you get 15 there. So we'll see what all this converts out to for everything. And quick recap here, we have Nicki Minaj looking at the peak here, and we have a magnifying glass on the peak. We're not interested in what's happening on this side of the peak. We're interested in the angle created between the time of occlusion versus where this peak is at. And this is going to tell us how much refraction there is versus how much refraction is predicted. All right, so, and as we continue the analysis, just keep that in mind because the numbers and figures that we get relative to the measurements for the occlusion are strictly going to be based on a refraction that is independent of terrestrial refraction as we go over a measurement that only differs from the predicted amount by 30 arc seconds, which is extremely small. And the amount of terrestrial refraction there was 2 arc minutes. So if that was affecting it at all, then they would have shown up in our occlusion timing, but it didn't. So anyway, astronomical refraction analysis of Pike's Peak. By using the tangent function, we can convert the angular differences into meters for our analysis. By using the Bennett refraction, which calls for 13 minutes of astronomical refraction, and the angular difference between the geometric peak and the star being 2 arc minutes, which give an angle of 233, the globe prediction for the geometric intersection should have been 2 degrees, 17 arc minutes per the doctrine of the sphere, which mandates a radius of 6,731 kilometers to create the 11 arc minute angular drop, which converts to 200 meters. When using the formula to predict the drop over distance, you can do the square root of the square of the radius plus the distance squared minus the radius, which will give you 200 meters in drop. And conversely, you can use a tangent function to based on the distance and the angle to the peak drop, which is based off of that as well, to get the drop to convert it into meters, which comes out to be 200 as well. So applying that same logic, we can apply any angular difference that shows up in these measurements. We can compare them to the observer and distance to the peak, which will give us the unit in meters, how much that's affecting the measurement. Okay, so what we do here is by comparing these two, we can analyze this in properly set context to the measurements and determine, if these measurements are valid and and do they meet the criteria of a valid measurement to determine whether or not the Earth is a globe or flat. So converting the values here, so 13 astronomical refraction arc minutes comes out to be 186 meters. When the measured difference was 2 arc minutes, that comes out to be 29 meters. The overcompensation is 216 meters when you convert that. And the geometric drop over distance for the globe is 200 meters. So they overcompensated by 16 meters on that. Now, look at this right here. We have minus 29 meters because it was over. So it created a negative in the prediction there. But what this shows us here is we were off by we were off by 39 meters. We were, so that, hang on, let me bring it up in the thing so you guys can see it. So I didn't include that. That's my bad. Okay, Pike's Peak, Regulus, 39. Okay. So over here, what was I about to show us? Oh, the difference. Okay, yeah. So when we go to derive elevations and distances based off of the occlusion angle and one of the other known factors, either being the distance or the occlusion. Okay. Coco, I saw your mic going off. I didn't hear anything. Were you trying to ask a question?
No, I'm having Discord issues. I'm so sorry.
Oh, no worries. Okay. Just making sure your mic was all right there. Okay. So Okay, so when we go to derive based off of the occlusion angle, the angle produced by the occlusion ends up being we're off because the true rise over run to the peak is 231, but we're off a little bit because of refraction. The actual occlusion happened a little higher than 231, happened at 233. I think the lowest one that Mike had recorded was 2 degrees and 32 arc minutes, but we often use the first one for the 33. But so the lowest possible that this could be is or like the lowest possible difference it would be 232 to and are predicted as 231. So that's pretty awesome there. But anyway, that angular difference converts to 29, essentially 30 meters, and that's what it's just a rounding error there. So this is where that comes from. This is why our measurements are off. They're quote unquote off. They deviate by the amount of actual astronomical refraction at that time, independent of any terrestrial refraction, which we'll see as we get to a measurement that was that has less than the amount of difference than the terrestrial refraction amount. So yeah, when we get into deriving the distances and elevations, we see how terrestrial refraction actually impacts the measurements. And we have explanations now for why, like the North Peak measurement, for example, is so far off on the distance. It's because of the lingering caused by the actual refraction difference, skews that in the measurement. The elevations are always pretty close, but what skews it is the on the distance the most is that actual refraction. So anyway, we'll get into that as we cover it. So to go back to the PDF here, now that we know that this that 233 occlusion timing is only 29 or only 30 meters different than our predicted time, that's it's safe to say that the occlusion timing happened with respect to the peak at 231 rather with 2 arc minutes of refraction rather than for the observer where the true position of the star is at 206 and it's being lifted up by 12 arc minutes. Because if that position were tenable again, this would create delays in the occlusion. They would have to then explain why, how they somehow have an extra 2 arc minutes of refraction to get over the peak. Like this, creates a multitude of problems for them as we continue. Let's see here. So we went over the numbers, went over that. Okay, note that the empirically derived astronomical refraction given by astronomical Bennett compensates entirely for the expected geometric dropover distance for the peak, a trend that will continue for all measurements and then some. All right, the lingering refraction. Okay, we'll come back to that. Okay, Blodgett Peak. So now we're going to analyze Blodgett Peak. Same conditions. So rise over run gives us 116 for flat Earth. Globe predicts 106. With refraction, they predict 108. For the apparent position at their location, the star was occluded at 109. So they're above the peak on that one. And instead of being aligned with it. And then we have, so the refraction, the primary part, the important part here, the refraction differences at time of occlusion. True position of the star at the time of occlusion was 111, and we predicted 116. It creates a separation of 4 arc minutes, which converts out to 59 meters, and we were off by 59 meters in our elevation derivation. So the astronomical refraction of 17 arc minutes gives them 181 meters of lift. Their dropover distance is 101 meters, and their astronomical refraction and overcompensation based off of the difference in the time of occlusion is 12 arc minutes, which gives 131 meters. So they're completely, as Mike was pointing out earlier, when they were going over, or when he was going over the 1/2 correction, compensating for that, this is how they're compensating for there being no drop over distance. It's the refracted amount, because if it's not, then there's no explanatory power for why the star is at that elevation. Okay, so the true refractive conditions at the time do not exceed the expected amount of drop over distance, so this qualifies as a valid measurement. So this is going to be important to understand, because if the amount of refraction exceeds the amount of drop over distance, how can it then be said that the Earth is a globe or if the refraction didn't make up the difference. The purpose here is to tell the difference, not go to somewhere where it's indistinguishable, and we'll see what that looks like as we continue on. Cheyenne Mountain is up next. Rise over run gives us 1.5 for flat Earth. Globe Earth predicts 53 arc minutes. When we get into the refraction amounts there, astronomical is predicted 18. The measured difference at time of occlusion was 5 with respect to the peak, and that gives us 13 arc minutes for the overcompensation. When we convert these into meters, their overcompensate, the refraction amount gives them 186 meters in lift, which compensates for their 142 meters of drop. The actual measured difference was a 65 meter difference at 5 arc minutes, not 18 arc minutes. So the real amount of refraction there was 5 arc minutes, giving 65 meters of difference. And the astronomical overcompensation given by that is 165 meters. So they overcompensated for 142 meters by adding 165 meters to it. All right, so again here, the refraction conditions do not exceed the expected amount of drop over distance, so this qualifies as a valid measurement. And the difference between the two, apparent position and true position, is 2 arc minutes here. Oh, sorry, that was something I skipped over on the last couple. So the difference between true and apparent there, because we're not considering the terrestrial refraction as Andrew Young's prescription, we have a 3 arc minute difference there between the peaks. So the hypothesis of the occlusions working out based on the apparency is not looking super good. So we're moving on to Blue Mountain here. Rise over run gives us 1.4 in degrees. The globe predicts 50 arc minutes. The actual measured time or location for the star at the time of occlusion was 1 degree, which gives us a 3 arc minute separation. And that creates a 16 arc minute overcompensation. The prescribed amount of refraction was 19. So when we go over the lifts and drops for that, the 18 arc minute refraction astronomical gives us 273 meters of lift. The drop over distance was supposed to be 294 meters, so completely compensated again. And then the measured difference at the actual time of occlusion was 3 arc minutes, so there was 54 meters of worth of refraction there rather than 273, and that overcompensated by 280 meters relative to the predicted 200 or 194 drop over distance. All right, this qualifies as a valid measurement because the drop over distance does not exceed the refraction amount. Then they're off by 2 arc minutes again on the apparent versus the occlusion there. Mount Rosa. Now this is an extremely significant one because we have the smallest difference in refraction to date. So here we rise over run to 1 degree 43 arc minutes. The globe predicts 1 degree 30 arc minutes. At the time of occlusion, the true position was 1 degree 42 arc minutes. And remember, we predicted 143. So the amount of astronomical refraction prescribed by Bennett is 15 arc minutes. The measured difference was 30 arc seconds. So the compensation was off by 15 arc minutes. They overcompensated by. When we convert those, when we derive the elevation based off of the occlusion timing and the distance, we're off by 7 meters. The amount of actual refraction was, what do you know, 7 meters. Bennett gives 205 meters of lift to a 170 meter drop over distance prediction, so completely overshadowing that again. And then with the overcompensation, it ends up being 208 meters. So relative to their 178 meter drop over distance. So the refractive conditions do not exceed the expected drop over distance. This qualifies it as a valid measurement. And we have here 2 arc minutes of separation for the apparent for the observer relative to the true position of the peak if there was drop over distance. Moving on to, and then so real quick here, what's significant about this is that at Mount Rosa, we'll pull out Mount Rosa, the standard refraction at the time was, Standard refraction at the time was, where did I move my thingy? Oh, shoot. Oh, there it is. Yep. Sorry. So the actual amount of refraction was 154. So basically 2 arc minutes of refraction of terrestrial refraction. And so if there was 2 arc minutes of terrestrial refraction, that would have displaced the star a little further than 30 arc minutes difference, or 30 arc seconds difference. So it would have been terrestrial refraction plus 30 arc seconds. And that wasn't what was measured. It was just the 30 arc second difference. So that's extremely significant because that shows that terrestrial refraction plays no part in the celestial and terrestrial occlusions. If it did, then the amount that we're off by, we could quantify it. We could directly link it back to the amount of terrestrial refraction. But it's not the case. It's not present. It's exactly, off by that amount, which gave 30 arc seconds and not anything to do with the amount of terrestrial refraction of 2 arc minutes. Okay, cool. So that further supports our case for not including terrestrial refraction. So the globular prediction for Green Mountain, as we continue, we only got a couple more, boys. We're sliding through these, I swear, but it's extremely important to go through all of them because it's just, it is what it is. Each one we learn something new. Okay, so Green Mountain here. Rise over run gives us 1 degree, 6 arc minutes. Globular gives us 51 arc minutes for the predicted position of occlusion with respect to the peak. The actual position with respect to the peak was 1 degree, 4 arc minutes. And our prediction was 1 degree, 6. This is a separation of 1 degree and 9 arc minutes. I should have just put 2 there. I should have just rounded that to, or no, it's 1.9. Anyway, definitely not 2. So one separation there, and then we have an overcompensation of 22 arc minutes because the refraction amount was 24 prescribed by G.G. Bennett here at a distance of 52,000 meters away. So what we get when we convert this into meters relative to the peak, we get a refraction lift of 366 meters with respect to a drop over distance of 217, completely overshadowed again. The actual amount of refraction at the time of measurement was 1 arc minute of astronomical refraction, giving a difference of 18 meters. And the overcompensation of 22 arc minutes gives a 348 meter, lift to what would be 217 meters of drop. So overshadows it, but it does not exceed the amount of drop over distance there. So okay. All right, and then the apparent separation there is 9 arc minutes this time. So when we look at the hypothesis of the apparent to the true there, it's off by the worst amount that it's been to date, which is the 9 arc minutes there. Then we have North Peak, which is rise over run gives us 45 arc minutes of a distance of 130,000 meters. And when the globe predicts 9 arc minutes for the physical elevation there, when adding for terrestrial refraction, we get 14 arc minutes there. The apparent position of the star was at 11 arc minutes. So with respect to that's for the observer position. So we'll come back to how much they were off by here in a second. Spoiler, it's going to be 2 again. Okay, so we go down here. We look at the refraction conditions, 23 arc minutes of refraction, measured difference of minus 13 because of the lingering. So we get 36 arc minutes of refraction difference for the overcompensation. When we convert all that into meters, we have a predicted drop over distance of 1,340 meters. We have a refraction overcompensation of 1,400 meters. And the actual measured difference was 13 arc minutes, which comes out to be a 500 meter difference. So Absolutely insane. And actually, I think I copy pasted that from the previous, so that's not the right. I don't think that's the right value. Give me 1 second. 255 converted to an angle. Yeah, that should be 800 and yeah, that should be 886. So this lift here should be 886, not 215. But anyway, again, the globe's off by 2 arc minutes. Here we have Getaway Mountain doing the same. Rise over Run gives us 53 arc minutes. Globe Drop gives us 39 arc minutes. I'm sorry, I said 53 arc minutes, right? 53 arc minutes for Rise over Run for Flat Earth, 39 for Globe on a distance of 48,000 meters, almost 49,000 there. The refractive conditions prescribed by Bennett are 23 arc minutes. The actual angular difference was 7 arc minutes of refraction, which creates a 16 arc minute overcompensation. When we ratio that out, it comes out to be 333 meters of lift for the refraction correction. There was an actual 7 arc minute difference, which comes out to be 104 meters. The overcompensation factor was 16, which comes out to be 230. And their drop over distance was 178. Again, overshadowed by their refraction. Drop over distance. So in this case, because we're not considering the terrestrial refraction, they're off by 3 arc minutes for the occlusion. So the observed prediction for Houndstooth here, we have Rise over Run gives us 10 degrees, 39 arc minutes. For the globe, we get 10 degrees, 36 arc minutes. For the time of occlusion, we have 10 degrees, 37 arc minutes. And for the refraction conditions, as per Bennett's prescription, we have 4 arc minutes. The measured difference at occlusion was 2 arc minutes. Dude, they're like formulaically just double us every time. It's hilarious. Overcompensation factor was by 2 there. Now we have 10 meters in lift over that distance. It's only a 5.4 mile distance there. So there's only I think it was like, what was it, 8 meters of drop over distance or something like that, or 6, something really tiny. But anyway, yeah, 6 meters. Yeah, so the astronomic refraction converts to 10 meters. The measured difference was 5 meters, and they overcompensated by 5, and which is more than their expected drop over distance, which was 6 meters there. Here we have them off by 2 again for the apparent position with respect to the observer. Now we have Old Blend Mountain, which are Jesse's measurements. Now we have Rise over Run to the peak gives us 1 degree 34. Globe peak gives us 1 degree 28 arc minutes. And the apparent position of the star at the time of occlusion for the peak was 2 degrees 21 arc minutes. Now we have astronomical refraction given by Bennett is 20 arc minutes. Oh, this is for a distance of 22,000 meters, by the way. And then the elevation difference between the two for the globe is 169 versus 607 for flat Earth. Okay, so the refraction converted into meters for this location is 131 meters of lift. Remember, the drop over distance was supposed to be 38 meters, so basically 40. Measured the actual measured difference, one of the largest numbers that we've seen, 12 arc minutes, and this comes out to be an 81 meter difference in the refraction measured. Now, here we have the refraction overcompensation being 49 meters. Now, this time, the refraction conditions do exceed the expected amount of drop over distance. So with this is an invalid measurement. This cannot tell us if the Earth is a globe or if the Earth is flat because of the amount of refraction here. It is completely compensated for the drop over distance and exceeded it, actually. And we'll take a look how this plays out in a couple other scenarios regarding Blend Peak when we see what happens when the elevation changes very slightly by 2 arc minutes in difference. So here they're off again by 2 arc minutes for the true and apparent there. Actually, oh wait, what do they predict for? Yeah, 28 and 30. Okay, yeah. So they're off by 2 arc minutes there on that. And then we go down to the second measurement now. Now, because this was a hill and each peak occlusion was tailored to where it actually intersected with the lower elevations of the mountain / hill, the occlusion elevation is slightly higher, is slightly lower for the time of occlusion. Instead of being uniform, like we'll see at Pikes Peak, we just use the same elevation for every peak. We just consistently use whatever the max rise over run is to the peak, instead of doing it that way, the way that it's compensating for every individual elevation change. But anyway, what we have here now is it's lowered by 2 arc minutes from the previous. So what the different, how this affects the measurement here when we get into the predictions, rise over run for flat Earth is 132, globe is 126. The occlusion happened at 119. The astronomical refraction from Bennett is 20 again, 12 arc minutes of difference now, 8 arc minute over comp. So we'll see how this affected the measurements now. So we have 20 arc minutes, 33 meters of lift with an expected drop over distance of 38. The measured difference exceeded the actual drop over distance again. So invalid for use of determining whether or not the Earth is flat or a globe using this measurement. And the apparent position was prediction was off, because not considering terrestrial refraction, again, was off by 2 arc minutes. Now, I'm sorry, the preface that I gave for the 2 arc minute difference for the elevation comes into play on the same mountain peak, but at a further distance. So on the same night at a further distance, when Jesse went to 42,902 meters away, this is where we see that difference come into play, where it's going to compensate exactly for the amount of drop over distance. Okay, so rise over run for this distance now gives us 53 arc minutes for a flat Earth and gives 42 for the globe. The apparent position was at 46 when the star was observed, because these are actually for emergences, not occlusions too, by the way. So just mechanistically the reverse of what we've been dealing with. So instead of being having to be below the peak to be occluded, this now has to be a certain threshold relative to the peak before it's lifted above it. So what's really interesting about this is because if you follow the 1-to-1 refraction mindset that was previously thought to be true, the star would emerge as soon as it's at 25 arc minutes below the peak, because then it's going to be above it. But what actually happens is the star has to get much closer to the actual elevation of the peak before it emerges. And that actual difference comes out to be 11 rather than the 26 or 25, which is what they would have wanted if the difference was 1-to-1. So there's a really interesting. So this is really interesting because it validates our methodology and use of the occlusion timings and monitoring it with respect to the peak, because that's the actual physical intersection that's dictating when you see the object occlude or emerge even. So really awesome contribution to the measurements there. So when we go over the predictions there again, it was 53 arc minutes for angle to the peak for flat Earth, globes 42, 26 arc minutes in refraction, measured difference 11, overcompensation factor by 15. When we convert that into meters, we're going to see that the astronomical refraction gives 300, or it gives 130 meters in lift. That's actually wrong too, I think. 1 second. Didn't put the right value in. Okay, the actual lift over, so there's 131 meters of drop over distance. The actual lift was 360 for that. So that needs changed to 360 there. And because that's just copied from the old value. And then the measured difference there, to make sure that's right, was 129. meters for the actual separation between the two. So actual refraction amount was 11, not 26. And this overcompensation factor converts to 177 meters of correction to what would otherwise be 131 meters of drop over distance. So again, here they've overcompensated by the drop over distance, by the refracted amount, by the actual refraction amount is 229, right? So 230, we'll just round that to 230. The drop over distance is 130. I'm sorry, I said 230, 130, 129. The actual drop over distance is 131. So these measurements, not valid to determine whether or not the Earth is flat or a globe based off of this, because the refraction amount compensates entirely for the drop over distance. So if that amount exceeds it, how can it then be said that the Earth is a globe, or that the Earth is flat based off of that measurement? If it's literally refracted too much to tell the difference, to make it indistinguishable, it compensated it exactly for the drop over distance. So invalid use of the theodolite, essentially. So as we continue on here, we have blend peak again. Actually, that one. We have the blend peak again, 53 meters. The true position being, actually, one second. Yep. Okay, so for the second one, this is the 3-cap star. So 53 arc minutes for the elevation prediction, no change there. 52 arc minutes for the globe. The occlusion time was 38 now with respect to the peak, because of the lower elevation location was used to be at 240, or to be at 42 there. So what that comes out to be is, I made the same mistake in copying it again. Oops, 1 second, lads. Okay, so the liftover distance, right, from celestial refraction was 313 meters over a drop over distance of 131. The actual angular separation at the time of occlusion was 14 arc minutes. That's a pretty significant, that's the highest one we've seen. And it gives 172 meters of correction to the drop over distance there, far exceeding the drop over distance. And the refraction overcompensation there is 140 meters. So refraction completely overshadowing what would be a globe measurement to facilitate the illusion of a globe measurement. All right, now we have Varley SE2 Squamish. That was Goose's measurement there. So we have the rise over run 4 degrees, 51 arc minutes. And then to the peak, we have, for the globe, we have 4 degrees, 4 degrees, 46 arc minutes. Sorry, guys, we're almost done. I know it's been a long one. I appreciate everyone being patient. Okay. True position at the time of occlusion with respect to the peak was 4 degrees, 47 arc minutes. Gives a 4 arc minute separation there. Bennett prescribes 10 arc minutes of refraction, and the difference there is 6 arc minutes. What we come out with is 49 minutes of lift, measured difference of 19 meters, or 20, you could say. Refraction overcompensation by 30 meters, and the drop over distance was 21 meters. And again, using the, not accounting for terrestrial refraction to compensate to lift, they're off by 2 arc minutes again. So the conclusion here is that the globe only exists as a mathematical correction to apparent position of celestial bodies, implying that the 69 mile per degree relationship has nothing to do with curvature of the ground, but rather some other optical phenomenon. Atmosphere equals dynamic. All computational models are based on statics, which each measurement in real time is a snapshot of those conditions, and it shows that that is not the case. Any questions, comments, or concerns, lads? I know that was a long one.
I still have my same question from last week.
Summarize everything Alan just said, though. Were you listening at all?
Before we continue, do you understand my position at all?
I just got home from work.
All right. Unfortunately, you will have to catch up to understand the position, and your question from last week will be answered. So we just went over was that we set the parameters for terrestrial refraction being included in the measurement. And what we found through Andrew Young's research and some other citations that he mentioned is that it is not appropriate to include terrestrial refraction in the astronomical occlusions to terrestrial features. And we went over all the measurements, and we went over the timing or the angular difference between the true position of the star with respect to the peak at the time of occlusion to determine the actual refraction amount. And what we determined was that it's nowhere near what is needed to validate what the globe says, and that it's not possible for it to be affected by terrestrial refraction, because one of the measurements we have at Mount Rosa, the astronomical refraction factor was only 30 arc seconds, and the terrestrial refraction was 2 arc minutes. So if terrestrial refraction played any role in the occlusion timings, then the measurement couldn't have been off by 30 arc seconds. It would have been off by at least 2 arc minutes, and then some other factor of the astronomical, which would have been the remaining 30, although we wouldn't have really known that at the time.
Didn't Danny Faulkner, the astronomer, famous astronomer, he's an anti-flat earther. Didn't he also agree that, or not agree, but he was confused as to why someone was incorporating terrestrial refraction when looking at a star?
Yeah, it's a gross mischaracterization of the two types of refraction, because like we went over earlier, astronomical refraction is dependent on variables that are not contingent on the variables that control the terrestrial refraction, because terrestrial refraction is bound to the boundary layer, which is where the temperatures affects the
humidity, temperature.
It affects things the closest to the surface, because that's where the heat transfers the most. But as you get further away from the surface, that transfer dissipates, and there's no relation to the effects on the ground to a path of light coming into the sky. And that was fully substantiated with the measurements that we went over.
Yep. So. And didn't he also say that, yes, indeed, celestial refraction is a curve fit formula?
I don't know if he said that, but we don't necessarily need him to confirm that. We have tons of I have tons of papers on how they derive the different coefficients. I mean, we have Bennett talking about how he curve fit them to the almanac. So, but yeah, they are.
I'm just using him as a reference because, as someone who doesn't have a dog in the fight, who just coming into Celestial, the Adelaide conversation, when I was talking to him, he immediately he said those two things and confirmed them. Very nice about it. This guy's an astronomer for like 30 years or whatever.
Yeah, nice.
So is that just? Oh, sorry, didn't mean to cut you off.
No, go ahead. You're good.
So is that to say that the terrestrial layer of the atmosphere has no impact on the apparent angle?
On the apparent angle of the occlusion, correct.
Yep.
I think it's incorporated into the astronomical refraction already.
Yeah, I was going to say it's incorporated into astronomical refraction. That bundles all of the atmospheric refraction together, right?
So if that were true, because it's just the coefficient output, it's not bundled into it. If that were true, then the measurement would have been off by that amount too. Like if it were and it existed in that, it would have been off by 2 arc minutes or whatever the refraction condition was. So no.
But like the terrestrial object's not gonna be affected by like something being occluded. It's just like whenever they like model the whole atmosphere, right? They're modeling all the layers. I mean, that's even contested how they modeled it, how they came to the conclusion. But like essentially all the layers of the atmosphere are being incorporated.
Taylor, you don't like applying Laplace's theorem for air mass proportionality to density so that you can make a spherical smooth gradient model based on statics and no dynamics so that you can make the curve fit? You don't approve of that, Taylor?
Man, you gotta do a presentation on that, Tigger.
It will be further incorporated into this. I just whipped this together over the last 3 days, so this is like a work in progress. But anyone that wants to review this data, like this is now the new meta moving forward. So if you're not providing arguments to refute what's in this document, then like you're not addressing anything related to the celestial theodolite at all.
I've got one more quick question.
What's up?
I won't mention the G word or coordinate transforms.
Oh no, we can go over those again towards the end, because there was something you said last week that kind of irked me a little bit, and you must be made to suffer now. So we'll go over that at the end.
So the question is, so you draw these triangles. What is the triangle and what is the real position of the star in these geometric diagrams that you're drawing?
A tangent to where the star was when it got occluded.
Yeah, but where physically is the star if you were to draw this diagram?
Wherever the star would be at the time of occlusion, it would be at that angle.
Yeah, but whereabouts is it? The angle's only part of the location of the star. Is
What?
the star very far away, or is it relatively close?
Are you asking me if it's 93 million light years or closer?
Oh well, anything. Is it?
I don't understand the relevance of the question.
Okay.
So you're trying to say the height of the star, or what are you trying to? What are you saying?
Yeah. Oh, yeah. The height will do. Yeah, the height and the distance.
Unknown.
The height is in elevation.
When the angle is 0 or negative. If you observe the occlusion at a negative angle,
Well,
where's the star?
Yeah, we actually went over that. So the negative angle would be that's basically an apparent effect because you're not on the ground, right? So you're not applying a dip correction, so you get a negative angle out of that. Mike actually went over that. He went to a place called, I can't remember the name, but if he's here, he can tell you about the negative one. Like we went over this a couple of Celsius ago. It doesn't.
Geometric proposition.
Well, the apparent positions of the stars, like everything we see is always apparent, whether how it sets is apparent. Like, is it going beneath our feet or is it setting due to optical reasons, just receding into the horizon? So the negative angle on both models isn't created by ball drop in this scenario of the occlusion. It's created by not applying a dip correction to being at the, above it. Because you're not on the ground, dude. Because the object that's occluding it isn't at the horizon either. That's why. It's an optical illusion. The negative angle doesn't mean anything.
Oh, so there's refraction happening that we're not covering in the other scenario. Different kind of refraction.
You said a completely different thing than what I said and introduced the word refraction. That's not what I said at all.
You said it's an optical thing. There's some optical thing going on. What other optical things would change that?
It's an optical illusion because the mountain peak isn't up at the horizon. The peak that's doing the occlusion isn't at the horizon, and you're not on the ground. You're above sea level looking at that, and it's bringing it up to the horizon. So it's creating the illusion of that. We went over this. Like a plane wouldn't be negative beneath your feet either. The same effect would apply. Like it's not... that's the answer to the question, and it's not a physically negative angle. That's it.
Well, it measures a physically negative angle.
Oh, no way. Based off of conditions that aren't being accounted for, that because there's an optical difference between you and the object occluding, or elevation difference between you and the object occluding. Like, dude, it's
well, even still,
like,
will tell you the angle will be negative, right?
I'm not saying that the angle wouldn't come out negative in that regard, bro. That's our premise. I'm saying it's not physical. It doesn't mean anything. It only comes out negative because you're not compensating for the fact that you're not on the ground and the object that's doing the occluding also isn't on the ground, but you're higher than it, but it's braised up.
Why does
that's
it
it.
Because it's still
it doesn't. It literally doesn't matter. It literally doesn't matter. We're happy to treat it as a positive angle. We don't care at all. You seem to think it matters.
Well,
I'll tell you what. Send me a PDF on why you think it matters.
Well, it matters because the star will be in or below the ground, right? If you observe and you've got a negative 1.5 degree or negative 2 degrees angle to the occlusion point, the star will be on the surface of the Earth a few hundred miles away from you. And that makes no sense, right?
No.
Well, it's a good thing it's optically based and all apparent and not physically meaningful.
But why is that any different to when it is physically meaningful when you do it for the positive angles?
Because we're on the ground, Dazza. The factor that's not being compensated for isn't there to create the discrepancy, bro.
I could go to Pikes Peak and observe back towards Heffron's place. I'd be looking downwards at a negative 1.5 degrees. And if the geography was right, I'd be able to observe a star setting behind Heffron's Place from Pikes Peak, right?
What?
The hell?
Yes, the answer is yes. And I've
Yep.
done that with the sun in a different location. I've filmed the
Yeah.
sun 1.3 degrees below eye level.
And I've
What are
got
you
a
talking
location
about?
here where I can look across two mountains that are kind of standalone, and there's nothing between the second mountain and the horizon at sea level. Same deal. You can get negative observation angles.
Is the mountain peak on the horizon? Is that the horizon? Or is there more to go?
Well, the horizon could
More to
be
go, right?
slightly lower.
Is there more to go or not more to go?
So the mountain peak is above the horizon, otherwise you wouldn't see it.
There you go.
All right.
There you go.
You're
Yeah.
all right.
There you go.
We've reached the conclusion there. Awesome.
How do we reach the conclusion? The angle is negative. The line
You're
of sight from the mountain is negative, which means
It's just
that
a tangent to an apparent position.
You can't have a
Oh.
tangent to an apparent position on a flat Earth.
bro. All right, dude. We can't have it. Okay. All right.
What?
Thanks, Daza. All right. Are there any questions in regards to what was presented tonight in regards to the actual argument where these stars are not being included at the globular angles, terrestrial refraction not being a factor to consider? Is there anything like that here? Because you know what happened last week? Like what irked me last week, what we went over with the coordinates and the projections, and you were like, no, you can just arbitrarily transform it without aligning any z-axis. So in order to substantiate that, Daza, I need you to find the z-axis. Like I need you to find all the transformations and show how the z-axis has a transform to it. Because if it says 0, then it's aligned. If it says numbers to it, then there's a transformation correction applied to it, then you're correct. If it says 0, then I'm correct. So the entire premise that all the coordinate systems are compatible with the geocentric coordinate system that we're referencing that's referenced for celestial navigation is all that actually matters. And when they do transformations, they have to be geometrically aligned per the z-axis. That's why when you look at z-axis corrections, there's no the correction there is 0, right? There's nothing being applied. So you have a history of contentiously just not acknowledging when you're flat out wrong and then just acting like you still have a position to maintain. So we just reached our conclusion with Beast again about there's more horizon behind the mountain. That's it. That's it. And then you're like, no, but still my argument, like we're not doing that. That's completely not on the table, bro.
I don't even really
Back to
understand
coordinate
his
systems,
argument.
right?
I don't even know what is your argument exactly.
So my argument is if your geometry that you draw of the mountain peaks and the timing of the angle, what does it all mean if the angle is negative? And the star is at ground level 100 miles away according to your drawing.
If the star is
Why
at
do you think
ground
it's at
level.
100 miles away at ground level? Like that
I don't know
doesn't.
what he's talking about.
For a 1.5 degree angle of declination from 1,500 meters, it's only a couple hundred miles, and that line intersects the ground if the ground was a flat plane.
Oh, bro, you're misconstruing our position and then conflating it and then asking why the star isn't where it's at.
Well, you're drawing geometric diagrams. I'm assuming that they're meant to represent where the star is.
No, do you see where Nicki Minaj in the corner of said diagram says, "This is not to scale"?
Oh no, it doesn't matter. It doesn't matter.
Oh, it doesn't matter. Sick, dude. That's tight, bro.
We'll still intersect.
It doesn't matter, dude. It's fucking great.
Line will intersect. But anyway, back to the coordinate transformations. Let's take a simple example, and we'll use a real one.
From Stellarium, bro. Not GCF to whatever the fuck. From Stellarium. The argument is specifically about coordinates in Stellarium.
That was about coordinate systems.
Nope.
Right?
No. Nope. It was about coordinate systems in Stellarium. And it was about, you were saying, well, there's different coordinate systems that they use. They use the barycentric, they use the galactic one, yada, yada. And that you said specifically that the geometric transformations are indistinguishable. I mean, arbitrary. They don't have, the z-axis does not have to be aligned. So I'm saying, find me some source code in Stellarium where they're doing a transformation and there's no z-axis coordinate alignment. And what that would look like, it would say, instead of saying z-axis equals 0 for the transformation, it'll say z-axis equals some angle.
So one of their primary coordinate systems is a J2000 based barycentric.
Do you have the just show me the coordinates? You don't even have to talk, bro. You can just show me what the coordinates are.
No, the z-axis to that is perpendicular to the ecliptic plane, and they transform those coordinates to a geocentric view, which means they've got to apply, the axial tilt component.
Just show me the z-axis corrections, and I'll acknowledge your point.
Oh, so in the transformation matrix, so what you do is
I said show me. I didn't say explain it and talk again. Your presence isn't required, bro.
I've got the source code open, but I'll find it for you. But in general, you can take any Cartesian coordinate system, you can translate it, you can rotate it, and come up with a new coordinate system, and the geometry doesn't change, right? So if you've got
Daza, you're repeating my premise, man. I went over a whole book of transformations of geometric shapes that give the corresponding transformations, show how they're all equivalent. I went through this last week, man. Like I said, just show me what your proof is. I don't need you to repeat the same thing. I lose my patience really quickly, like when that happens, man.
I suspect it's in your book, right? The z-axis can point in any arbitrary direction, right?
Can I ask you a question, Daza?
Yeah, sure.
Can you explain how the globe coordinate system maps to the flat Earth coordinate system and vice versa?
What flat Earth coordinate system are you talking about specifically?
Well, we're using the same coordinate system, but obviously interpreting the data the same way because globe Earth advocates interpret it as coordinates around a globe, whereas flat Earth advocates interpret it as coordinates on a topographical plane. And you describe to me the difference and how one maps to the other, because in so doing, you'll answer your own question about how negative goes below the horizon on a globe, but it does not go below the horizon on a topographical plane. So I'd like to hear your explanation of how those coordinate systems map to a globe versus a topographical plane.
So typically, the topographical plane is using some kind of projection, right, to transform the spherical coordinate system of the geometry of a globe into a plane, breaking the distance relationships along the way. So lat long.
Well, wait. Let's stop there because you say it's breaking the distance in the process, but we don't agree on that. In fact, I think Shane could probably do a really great explanation of how the topographical plane versus a globe maintains the same different distances, the same latitudes, the same longitudes, the same angles.
Okay.
The only difference is how they are interpreted in a globe view versus a topographical plane view.
So in the globe view of lat long, if we go to somewhere like Australia, because you'll have to pick a projection, Mike, right? And then match it to reality. So if you come to Australia, we're about 30 degrees from bottom to top and similar width. And the lat long grid, when drawn on Australia, has very specific distances between all of those things, which are verifiable, right? You can actually verify that all those distances across Australia, as per a Mercator projection centered on Australia, you get that kind of overall perspective. Now, when you say projected onto a flat plane, what kind of projection are you talking about, and where is it centered? So that I can measure.
Well, who verified them? Who verified these values, Daza? If you don't
He's
mind
just
me asking.
saying we're both using spherical coordinates. That's all he's saying. We're interpreting them differently, right? We're saying we all observe half a hemisphere. That's what the coordinates are based on. Fulfilling that second half with a negative value is just conceptual math. It's based on the circumference value, which is the circuit that the celestial object does, right? I think that's what we're trying to say. But did you have actual questions, Dazzler, or did you just going to do your regular thing?
No, I just asked a question. So I've got two sets of coordinates that I can deal with in Australia, right? I've got lat long, and clearly lat long, the dimensions of lat long in Australia are different to the dimensions of lat long in 42 North if you've got some sort of projection, right? So there's no flat Earth mapping of distances that makes any sense, that is consistent 42 degrees north and 42 degrees south.
Oh.
So you need.
But they are consistent to the spherical coordinate system in which we're using, right?
Is it the same coordinate system that we're using, bro? Because that's what our premise conclusion is. But yeah, if there's anything related to the actual celestial theodolite process now, and also Daza, just send me a tag when you find the correct transformation to Instagram or whatever.
18 weeks and nobody will address the actual point. This is getting more than frustrating.
Well, to be fair, hold on. We did just introduce a new analysis based on the refraction conditions. So I expect it will take a week or so for the globularists to take it in, soak it up, and come up with refutations. But it does not look very, I'm interested to see what they have to say, honestly, because I think this is the finalized form of the argument. We've really reached our maximum potentiality for a conclusion here. We've extracted everything we can out of the measurements in regards to, what creates the occlusion, the refractive conditions, different ways to derive, how much drop there is to the peak. Like there's some things that we've all agreed on over the course of this process that we're all in agreement now, such as like how much drop over distance to the star there is, how much drop over distance to the peak there is, et cetera, et cetera. So we've come together on some fundamental things, I think, which is really nice. But yeah, this will require its own, refutation to it. So I don't expect anyone here to pick up a mic right now and just be like, yo, son, you X, Y, Z. But yeah, a lot of the argumentation put forward from the Globe lads over the last couple of weeks, they've solidified their position, made it very clear. We went over John's, not just, I'm saying John because he puts it forward the most, but it's the mainstream Globe position, essentially, right? No one else is going to argue that, I don't think any other globularist would say that refraction doesn't lift things up 1-to-1. That's pretty well accepted. And mathematically, if you were to work out the conditions to make this match under the premise put forward, it would, it has to lift it up 1-to-1. So yeah, showing that isn't the case, unrelated, it's extremely significant and will be hard for them to overcome.
Shout out to Andrew Young.
Shout out to Andrew Young, dude. Went over the whole history of it. And so there's like a history of geodetic surveyors that were like, hey, when we're close to the horizon, can we just celestial and terrestrial refract? And it never worked out. There was 2 major instances where it was applied and rejected, didn't work out. And yeah, it just doesn't, there's no actual way for them to model it. And then even in the papers where they're going over, how to compute the conditions and whatnot and how they model it, they're like, man, it would be really nice to have some actual quantifiable temperature and pressure measurements and stuff, because like how they have like the lapse rate here terrestrially. Well, they assume a uniform lapse rate to create the refraction conditions to lift everything up and all that, but that's completely different than the conditions where that thermal transfer from the surface isn't taking place or having that much of an effect. So the temperature and pressure conditions between the star and the peak are not even close to being the same as what they are on the ground.
So Mr. Young just basically put forth that conflating astronomical and terrestrial refraction is misleading and scientifically like inaccurate, particularly like for like low altitude observations where the
Yeah,
variables of
yeah,
lower atmosphere have dramatically different effects on the two phenomena.
100%. And not only that, that premise was substantiated with the Mount Rosa measurement, where the astronomical conditions only facilitated a change of 30 arc seconds, whereas the terrestrial conditions would have dictated 2 arc minutes of change.
Right. I saw that. That's cool.
So the PDF is available in the text chat there, and I will get this uploaded on the Obsidian database. So I'll put a link here to that when it's uploaded, and you guys can reference that. But yeah, everything is laid out in such a way, and when this is done, the reader should be able to read this and have all the information necessary to interpret the argument and understand it to completion. There's a definition. We got definitions over here. We got a definitions tab I'm building for everything. So everything will be self-referenced within this. And then you could just come here and learn all about the celestial theodolite without having to watch endless hours of, what do you call it? Updates.
Thanks for all the hard work, y'all.
No worries, lad.
My voice sounds a little funny. It's hoarse, but I would love to get this before people who aren't as emotionally charged about globe versus flat, like astronomers or classes that can break it down, analyze it, look at the data, because all the data's there. It's transparent. It's all available. I'd love to get some other eyes on this, but thanks for all the updates.
If you think the data is transparent, I would love to go over it with you because I've got some issues with the data.
It seems like the issues are possibly that refraction has been found out. Like what refraction was used for to create a sphere that people live on, even though that's not true. But what do you have to talk to Alan and Dr. Mike about right now that would be clear and to the point on what they presented, the actual celestial observation, the method?
Well, before he answers, keep in mind that he wasn't here for my presentation at the beginning, so he doesn't know that we've
Or mine.
established beyond a shadow of a doubt that refraction is exactly equivalent to half the curvature of the Earth when
So,
it's perfectly adjusted.
Okay, so you got to get caught up, and
well,
then maybe next week come back.
okay, well, let me ask this then. This is just simple. Is it still the claim that arctangent of rise over run will match within a reasonable certain margin of uncertainty the atmosphere off at peak altitude angle given by stellarium? Is that still the claim?
Always has been.
Okay, that's what I've got a problem with because that is not true. It does not always match. That is my problem.
No way.
Yeah, I just shared.
Is it off by an amount that is the amount of refraction? Jesse, you got to get caught up, my dude.
Yeah, you can't wander halfway and 3/4 of the way into the movie and just miss all of the presentation and then expect.
Well, to be fair, it's not like he listens to what you say anyway, so it's fine.
Well, that
is true, but
is it also true that so far no angular margin of uncertainty has been stated that would allow the null hypothesis to be refuted?
Oh, we have the actual refraction conditions now and what constitutes as a valid measurement. All you need for a valid measurement is for the actual refraction conditions to not exceed the amount of drop over distance expected. Because if the amount of actual refraction conditions at the location exceed the amount of drop over distance, you can't conclusively determine if the Earth is a sphere or if it's flat.
Well, in other words, like let's say in the case of Pikes Peak.
Did you hear what I said? Did you hear what I said?
I'm asking
not in other words. I said something and then you said a different thing. Do you understand what I said?
Well, I need help understanding. I need to ask
Okay.
a clarifying question. May I?
Okay.
Go back and
Yeah.
watch, Jesse.
Okay.
There
Okay.
you
One.
go.
Okay. One second. 1 second. You can ask a clarifying question. However, I can pull up an exact quote of you telling me how the refraction measurements are produced and you explaining the exact ratio. So you actually know exactly how. Would you like to refer to you telling you how, or do you want to continue this line of questioning?
Well, the discrepancy here is like, let's say.
Do you want to hear you tell you, or do you want to continue this line of questioning?
See, Boston Bear, here's the problem. They won't let me address the issues because they do not want you to know what the answer is. That's the problem.
Jesse, you missed 2 hours of a whole presentation. You're coming in with the same horse shit you say every time. You got to give us a break, man. You got to just take a step back.
I'm about to read the quote from you. Give me a second. Let me find it. I'll just read to you explaining to. I'm going to read to you explaining the same what I'm explaining now. I'm going to read you explaining it to be months ago, bro. So unless you by happenstance didn't understand what you were telling me, which would be kind of crazy, that'd be weird. But let's see what we got here. Give me 1 second.
I was going to say, while you're looking that quote up, I wanted to say, in my years of investigating the truth of our realm, we've talked about the azimuthal grid of vision, the dome of vision, the perspective of how we see things, the limit of our vision, vanishing point. All these things were like the globe believers were just like, nuh-uh, or like just talking around it, obfuscating, just but basically laughing at us for bringing up these words, saying word salad. Now that we have the celestial theodolite, it's just hard facts that we see that the way the celestial bodies present to us is like half a hemisphere, or we have a limit to how much we can see the sky. And when it disappears, it's not because of the a globe that we're living on. It's just pointing more and more that we live on a plane, a topographical plane, and they don't want to accept it. So now we just stick with what you're doing. You're sticking to the data. You and Mike are working hard on making sure this is exact. Actually, the anti-flat earthers are making your argument tighter and tighter and better and clearer. That's why I'm wanting people that aren't emotionally charged to look at it. Like I'd love for Skiba or what's his name that was going to work with Dave was wanting some proof to go over. Anyway,
Eva.
That would be good to get more eyes on it because it's a tight
science.
ship now.
All right,
That's science, man.
All right, real quick.
Getting it tighter.
Real quick, we have from Jesse a couple of months ago in July, I think, or June. And I asked him, the question posed was, can you find...
Show us the whole conversation. When
I
I
don't-
say because it's...
Listen, guy, I'm about to explain the full conversation. I have your quote from it. Shut the fuck up and let me finish talking and start interrupting me, bro. So what the question posed was, I had asked Jesse if he could find me a location at in Utah for an occlusion with respect to some peak. I can't remember the peak's name, but he said that he couldn't do it. And I asked why, and he said, and this is his response now. So he says, because it's too high compared to the observer, and the observer is too far above sea level. The higher the elevation, the lower the atmospheric pressure. Now, it's funny that he all instantaneously remembered what he said after he was just like, oh, what do you mean? Let me ask you all these more hypothetical questions. Dude, so hilarious. Anyway, the higher elevation angle and the lower atmospheric pressures, the less atmospheric or astronomical refraction there is. The method relies on turning off atmospheric refraction to get globe results. And if the elevation is too high, not big enough, then the change is made by turning off atmospheric refraction to lower it will not be enough to match the globe. If we look at the formula, we can see that both the flat Earth and globe require the subtraction of atmospheric refraction. That's not true at all. God damn it.
Jesse's not listening to you. He's typing right now.
Oh, I don't care. That's completely fine. This is just standard operating procedure. He wasn't listening when I explained it and then was trying to feign that he didn't know as I'm literally quoting him, knowing exactly what, like, he knows exactly what is being talked about and discussed. And then as we started going over it, he was like, no, tell the full context, as I was trying to tell the full context. Insane.
Isn't it also ironic that John is also typing right now instead of listening to what you're saying?
Yeah, and they always will. Their position was entirely refuted earlier. John was here the whole time. There's no refutation to it. So the method relies on turning off astronomic refraction to get globe results. So the elevation, it can't do that if it's not low enough to match the globe. If we look at the formula, we can see that both flat and globe require the subtraction of astronomic refraction. And this is his formula, right? This isn't the formula. This is the formula that he made for a simulator to get the globe Earth angle without, quote, using the flat Earth angle, because there was this weird thing that happened where he had to circumvent that. So anyway, this is for him, his derivation to subtract and add these things to make the prediction right. We don't have to do that because that's part of our premise and fully substantiated in the measurement. But anyway, we're going to get to the ratio here of what produces a quote unquote globe measurement and why it doesn't count as a valid measurement, because what you have to do to get the globe measurement makes it so that you can't distinguish between refraction and the globe result. So here we go. Continuing on here. If we look at the formula, we can see that we both require subtraction of atmospheric refraction in the apparent lower angle. But if you're higher in altitude, there's less astronomic refraction there, and you need a higher elevation for the mountain, which corresponds to the angle not being compensated by the refraction amount. The exact thing is aligned with the globe so this is how you create a globe measurement, when the globe or when the angle to the mountain minus astronomical refraction plus terrestrial refraction is equal to the arctan of rise over run minus the globe drop over run. So what we looked at earlier was this exact condition played out in 3-cap. We have a rise over run for flat Earth gives us 53 arc minutes. The globe predicts 41 arc minutes. The time of occlusion with respect to the peak was 38 arc minutes. Now, when we get into the refraction correct conditions here, they say that there's 26 arc minutes of refraction. Now, the actual separation at the time of occlusion, in other words, the actual amount that the star had to get lower to relative to the peak before it was occluded, before it was physically intersected, was 14 arc minutes. That's a pretty significant amount, but it is nowhere near the 26 that is projected from the Bennett figures. Now, if you convert that into meters, that creates a meter difference of 172 meters. So you can think of it like the star had to be 172 meters below the peak before it emerged. I'm sorry, because this was an emergence. I keep calling it an occlusion. So the star here had to be within 172 meters before it was visible. Now, what this creates is an overcompensation factor because of the actual emergence versus the predicted emergence based off of the refraction is 11 arc minutes difference, which is essentially creating 140 meters. Now, this number is less important. It's this number right here, because this is the actual amount of refraction that lifted the star and or caused the occlusion. That's what we found with Pikes Peak and all that, because we're always off by the refracted amount, because that's what creates the difference in the apparent angle. So anyway, this number right here, 172, is larger than the 131 number, which is the number for drop over distance. So the amount of refraction is completely overcompensated for. It's greater than the amount of drop over distance. So this measurement can't tell us if the Earth is a globe or if it's flat, because the conditions on which the star emerged among the peak were completely facilitated by astronomical conditions that take Earth curvature off of the table. And so if your measurement of a globe only exists as a specific ratio per measurement in specific locations where it would only be possible to get these kind of refraction conditions to offset it, then the Earth is not a globe and your contention is meaningless to me.
So are you saying you do have to apply some, by your method, have to apply some refraction correction to atmosphere off at peak to get the correct geometric angle? Or is atmosphere off at peak the correct geometric angle?
Atmosphere off at peak is always the correct way to make the prediction. What's measured, right, is a difference between the prediction and reality. And when we take that difference, what we find is that that's the actual amount of refraction that caused the difference. That's why it's off. that the astronomical refraction value causes it to deviate. So for the example of Pike's Peak, for example, right, we predict 231, but the occlusion timing puts the star's true position at 233 with respect to the peak. Well, how did that work? Well, it was refraction. The difference between those two lifted the starlight over it until it was 2 arc minutes below the peak, and then there was not enough refraction conditions between the starlight and the peak to continue lifting it over, and it became occluded at 6:43:07 p.m. So I'm not saying that there's no refraction, doesn't exist. I'm saying that in order to make the prediction, you don't need to account for it, and it will it's either going to closely match flat Earth or globe. But then when you do the measurement, what you can do after is you can find out how much refraction there was, compare and contrast, and you can also set a parameter for what constitute as a valid measurement. And for example, if your refraction, if the actual refraction value exceeds the amount of expected curvature, then it can't determine if the Earth is flat or a globe.
So Greenhorn Mountain, using your method, assuming no refraction, came out 2,000 feet too high. What caused that 2,000 feet extra height, according to your method?
I have no idea what you're talking about. I'm on Green Mountain right now. I have a rise over run to predicting 1 degree 6 arc minutes. I have an occlusion separation of 1 degree and 4 arc minutes. So that's the time of occlusion. We derive distances and elevations based off of that. For elevation, we get 994. The actual elevation is 1,012. For distance, we get 53,000. The actual distance was 52,000. And for the globe gets, let's see here, they get 794 for elevation, and they get 67,163 for distance. And for the refraction amount, they have 23 there for 23 arc minutes. And when we convert that all into meters, that gives a lift of 366, and they expected 217 for drop over distance to create the 51 arc minute prediction there. And then the actual separation between prediction and measurement gives 1.9 arc minutes, which translates into 17 meters. And the 17 meters is less than the drop over distance, so we're good there. And the overcompensation of that comes out to be 22, which gives us a final total of 348 meters of refraction overcompensation. When you say it gives an elevation of 2, what are you talking about?
Greenhorn Mountain or North Peak.
And you actually already explained the answer to Jesse's question.
I know. I'm gonna do it. I know. I'm gonna do it again.
Sorry. Okay.
Spoilers, Mike. Spoilers. Okay, so here we have iPuppus. We got a rise over run, 45 arc minutes, a elevation derivation of 2,200. The actual elevation was about 1,700, let's say. So we're off by 500. We got a distance of 130,000 meters. We derived the distance of 100,000 meters. We were off by 30,000. The globe predicts 35 arc minutes for true elevation, derived an elevation of what did they derive for? 350. So they're off by 1,341 meters, and then for distance they're off by 6,000. What's that?
I said, sir. You've got. You're showing 516 meters of difference between arctangent of rise over run and altitude or atmosphere off at peak for that one. Is that right?
Where at? Are you saying that?
E6.
That is the difference in the elevation derivation. So we derived, based off of the occlusion timing and distance, we derived an elevation of 2,208 meters. So the 516 is the difference from the true.
You're chopping up a bit there, Alan.
Oh, 1 second.
Not for me.
Oh, okay.
Okay, good. Just for me. Good.
So that 516, if you actually averaged all your data points, I think it would be closer to about 2,000 feet worth. But let's just say it's 516. That's 1,600 feet of error. What caused that error?
Oh,
right?
yes, this right here. So you see the actual refraction amount is 13 arc minutes. So that's the actual difference between the true position of the star and the physical elevation of the peak at the time of occlusion. That lingering effect is what causes the offset.
Well, hold on. I thought this method avoided all influences of refraction. Is that not true anymore?
Man, you really need to watch the presentation.
As
Well,
Jesse, as per the measurements and the prediction, we ignore them all entirely. And when we have the cases where things are in the most, because the refraction differences of elevation, when we're 1 degree or higher above the horizon, right? There's less. When we're at these angles where we're 1 degree and sub 1 degree, right? Like right now we're doing an elevation that's predicted to be, sub 1 degree there. The actual refraction conditions come into play, and that's what's affecting the measurements. Now, we didn't know this at the time when we started this, because for Pikes Peak, for example, and for most of them, the angular separation is only a couple of arc minutes. So we didn't realize that was what was causing, that's the actual refraction amount. So when we're quantifying that, and now that we've done that and understood it, you don't need to account for it when you're making the predictions and stuff. But when you're doing the comparative analysis afterwards, you can see how much refraction there was, how much there was predicted, and you could ratio these out to convert them into meters to see how it affected the measurement in terms of like lift in meters, which helps me think about it easily.
Oh, so when I time an occlusion, I use stellarium to get the atmosphere off at the peak angle. That's not the true geometric angle to the mountain?
Sorry, say that again. When you use the observer location peak off or atmosphere off?
Atmosphere off at peak at the time of occlusion, is that altitude angle, atmosphere off at peak in stellarium, is that not the true geometric angle from my position to the mountain? Mic check.
Oh, sorry, my mic was muted. So is the star's true position with respect to the peak going to be the same angle as it would be to the observer? Is that what you're asking?
No, that's not what I'm asking. No. Let's say I time an occlusion.
Right.
I put stellarium on the peak, set it to that time, set it to that star, turn atmosphere off on the peak in stellarium.
Right. Yep.
Read the altitude angle. Is that the geometric
yes
elevation angle from me to that mountain?
Oh.
Or do I need to apply a refraction correction?
So that angle, right, it's going to be off a little bit by the actual astronomical refraction amount, which we've quantified after the measurement, but we have no way to predict how much actual refraction there is beforehand, if that's what you're asking. So if you wanted if you wanted the exact time, you would have to get that. If we're saying, hey, this rise over run comes out to be 45, and then on a globe it comes out to be 35. If the stars is it closer to us or is it closer to you? And then from that we derive distances and elevations and look at refraction conditions for the analysis. So
okay, yeah. Thank you for helping me with this. So that DMS in F3 or E3, the angle in E3, is that the that's the arctangent. Where's the value from stellarium? Or the stellarium simulator?
Who?
The atmosphere off at peak.
Atmosphere off at peak is represented over here with 58 arc minutes.
Okay, so is 58 arc minutes and 4.8 arc seconds, whatever that is that the true geometric elevation angle from that observer to that mountain peak, or is that disturbed by astronomic refraction?
It's disturbed by 13 arc minutes of astronomical refraction.
So that's why I asked earlier if the atmosphere off at peak was equal to arctangent of rise over run, and now you're saying no, it's not. You need to add in astronomic refraction, right?
The deviation in the measurement from prediction will be caused by atmospheric refraction.
Okay,
Can I
so
jump in here, Alan?
Absolutely.
So Jesse, I can tell you an easy way to resolve your dilemma, and it does not require, although Alan has tracked it to atmospheric refraction. You don't need to account for that. All you need to do is look at what the globe Earth angle is from the observer's location. And do you have that on this spreadsheet somewhere, Alan?
Yes, the globe prediction angle is 50 or 35 arc minutes.
Okay, so what you can do, Jesse, is calculate the altitude that corresponds to that angle, and then subtract from that what you predict the apparent height of the mountain is, which is off by 1/2 the uh, distance angle. And that will give you a common mode error that's common to all measurements, regardless of method. And then you can calculate the arctangent of rise minus that deviation overrun, and that will give you the true angle that Stellarium reports is 58. But it's in this particular case, I think it was off by how many? 516 meters.
Yes.
Or am I thinking of another one?
We were
Okay,
off by
so basically,
516.
yeah, basically what you do is whatever the globe Earth uncorrected angle says, subtract 516 meters from that, and that will give you the true globe Earth angle. Whatever the flat Earth angle, what basically uncorrected angle at the peak says, subtract that 516 meters from that, and that will give you the true globe Earth height. And you will find that they match within a fraction of a meter every time. And in the live stream chat, I put a little graph that shows that for you. And I think when you read Alan's PDF and you read my PDF and examine that graph to see what it's telling you, you'll figure this all out. It's pretty simple. It's easy to compensate for. And Alan did a really excellent job of how atmospheric atmospheric refraction is causing this common mode error.
Astronomic.
Astronomic, sorry. But all you really need to do is subtract the common mode error, and then they're both as right as rain.
So, am I understanding correctly that every flat earther that wants to use this method to measure the height of a mountain has to use globe drop?
Nope, that doesn't make any sense at all. All you do is rise
Not
over
me
run to
neither.
wherever the peak is, enter the observe the occlusion, go to stellarium, see where the star was at. The deviation, it's either going to be closer to flat Earth or globe, and the deviation from the two is going to be related to astronomical refraction. That's it. The way that you're trying to reframe it as if there's like a different thing or different process, you've now somehow said, well, we don't have to account for astronomical refraction, but we globe drop this time. Like, this is getting tiresome. You're like,
Well, I'm getting mixed signals here. Like, my question is 0, 58, 4.8 the geometric angle to the mountain peak? And at first I thought the answer was yes, and now it sounds like the answer is no, that I need to add
yeah.
or subtract astronomic refraction.
So listen, big dog. Either way, right? Even if you didn't account for astronomic refraction and you just took the occlusion angle as is and you drew a tangent to it, that tangent doesn't belong to an angle that corresponds to numbers that are going to be able to produce globe measurements. So that's the actual point. So this weird roundabout thing it doesn't refute anything about the process or anything.
Never mind the globe. Let's say I'm a flat earther. I'm out hiking. I see a mountain. I want to know how high it is because I want to climb it someday. I want to know how high it is. I know geometry. Okay. I know the distance. I figure that out somehow. Can I use a star occlusion to get the geometric elevation angle to that mountain? And if so, what is that exact formula and method?
Yes, you just need to know the distance already, and then you have to have the occlusion timing, and then you can derive the elevation off of a tangent function. So you can do the distance times the tangent of the occlusion angle, and that will give you the elevation in meters.
And what do I put in for the angle, the 58 4.8?
You put in the position of the star with respect to the peak at the time of occlusion, atmosphere off.
Which is the 58.48 there, right?
Yes.
So when I do that, for Greenhorn Mountain, I get an extra 2,000 feet, which is significant. So why is it wrong? So I'm not doing the formula right. Something's wrong.
Are you talking about North
What you're
Peak?
calling 2,000 feet is 516 meters.
Yeah.
Well, 500.
Yeah. Oh, yeah, Jesse. That's the full elevation of the, like, that would be that would be the elevation. So
no,
what are you talking about?
516. No, 516 meters is about 1,700 feet. Okay, if you average all of the Greenhorn Mountain data points, it's actually very close to 2,000 feet. But let's, for the sake of discussion, you've picked the low, and that's okay.
Yeah.
When I put in that atmosphere,
I picked,
that peak,
bro. I have all three of them. Which one would you prefer? We can do that one. Since you want to try and take a cheap jab, what's the low one, dog? The 5. Okay, we got 58, 43 arc seconds here. We got 58, 43 arc seconds here, and we got 58, 4 arc seconds here, bro.
I can see if I can find.
So, why do you try to sneak in like a thing like I'm trying to do something sneaky, bro?
He's not sneaking in anything. He's just asking questions.
No, he's not. He said since you tried to pick the lowest one, as if I tried to pick it because it's favorable or something. I can do all three.
Do you have IPUP?
Yes. Which one? There's IPUP and IPUPus. You want IPUP? IPUP's the first one that's up. That's the one we're looking at.
And Jesse, if I can add, the other thing you're doing wrong is you're trying to average them. And if you notice, Alan's showing a different celestial refraction for each one. So you can't average them. They're individual measurements that each have different affecting factors. So you can't just average things and call it good.
Such a good point. The atmosphere is not static like they've modeled it and told us. It's dynamic. Changes per second. Each one of these measurements, 1 second, is a snapshot of the dynamic conditions at the time of flight for the light as it got occluded by the peak. So anyway.
Okay, so in my spreadsheet, the average for hikes
you say go ahead.
In my spreadsheet, which was made from your original spreadsheet, using math that I know is correct, most of them are either like 1,800, 1,900, some of them are 2,100. Somehow your math is different than mine, but that's okay. Let's just say for the sake of discussion that I record the occlusion timing of that star. I put the atmosphere off at peak angle 58 4.8 into tangent times the distance. I get 1,600 extra feet. What is causing that? Obviously I need to do something else to get an accurate height. That is not the correct height, right?
I have no idea what you're doing differently.
It's okay. We can go over that if you want. But even your 1,600 feet here is
what were you saying, Mike?
A big
Hang on a second. Well, 1 second, dog.
So Jesse.
Yeah, the purpose isn't to get it. Sorry, go ahead, Mike. You go first.
Subtract the value in J17 from the value in B15, and that will give you the actual angle.
So what I want to know. Okay, so I take I take the 58 4.8, and then I subtract from that the 1337 or 1334.7.
Sir.
Exactly.
Oh, and then that will be the true geometric angle to the top of the mountain.
And you have to do that also to the uncorrected globe measurement from the observer's location to make it right. When you do that, you'll see they're both right in their own worlds because they have a common mode error of that amount of refraction.
Ooh, I
Right.
didn't even think of doing that for that.
Yeah, I don't care about the globe right now. I just want this
Yeah.
to work on the flat Earth, right?
Yeah, it works.
So
It works on both. And you're saying that the factor that's present in the measurement is doesn't matter what you believe in. It's present in both. Anyway, continue.
okay, so just I'm gonna open a notepad and write some stuff here. I want to make sure I'm understanding this. So I do the original method. I get the occlusion time, atmosphere off at peak, and then I subtract astronomical refraction, right?
Well, you're not going to know the astronomical refraction yet, so you have to subtract the difference in position between the true position of the star and the elevation of the peak, like the true elevation of the peak.
Okay. All right. So okay. So step one is still get ATM off at peak, right?
Yep.
Okay. And so what's the next step? I subtract. What do I subtract?
The position of the star at the time of occlusion with respect to the peak, and you subtract that from the rise over run of the elevation, that which gives you the angle to the peak from the observer.
So I'm subtracting the star's altitude angle from stellarium at the peak from what again?
From the elevation of the mountain derived by rise over run.
Well, what if I don't already know how high the mountain is?
Well,
can
then
I
you would
measure?
I'm sorry. You were trying to do it backwards. Yeah. Sorry. So you would have to use your distance. Sorry. Yeah. So you occlusion timing and the distance. My bad.
Okay. So step 2 is what? Take the tangent of the
distance times the
atmosphere.
tangent of the occlusion time.
Okay, let me actually share my screen if you want to watch to make sure I'm getting this right.
I
And
mean,
I'll
bro,
save it and I'll share
you
it.
can just look at my screen share and look at the formula. You can just go here and copy the formula. You can just do any of these things. This is basic principle stuff that we've been going over for like 17 weeks.
And this is new. This is something new, it sounds like.
No, deriving distances and elevations started in Celestial Theodolite Update 4. This has been the argument for a hot minute that has never been acknowledged and has gone unanswered for the entire time, other than like, oh, you're doing the trig wrong. You're, just like basic hand wave dismissals. This has always been the argument. And it's like 17 weeks into this, kind of getting frustrated that you're like, let me ask you all exactly how to do this and write it down this time for realsies. Let me do you one better, dog. I will write this is already written down in a guide in the PDF, so you can just reference that. It's been about, let's see, we're coming up on 2 hours and 18 minutes. So we've reached our maximum amount of airtime today. So we're going to wrap up. So let's get your final thought out here. And then if your notepad isn't complete, you can refer to the PDF that I dropped because it has the exact instructions in it. You can also reference this update at the beginning. I go over it. It's all in there. And then you're not what I would call a foolish man. So you can also reference the spreadsheet there and just look at the function used. It's all pretty basic. I'm sure you'll get it. So go ahead and get your final question in, and then we're wrapping.
Okay, so as step 2, I have take the tangent of atmosphere off at peak altitude angle, multiply it times the distance, and that gives you the delta height of the mountain.
Yes, sir. But that looks correct.
Okay, so now we know that's not correct because it's 1,600 extra feet in the case of Greenhorn. So what's step 3 to make it correct?
Step 3 is now seeing how much astronomical refraction there is. So you subtract the difference from the true position of the star with respect to the peak and the elevation or angle of the peak that was derived from rise over run.
Well, but if I don't already know that. Oh, so I subtract.
I can make it easier for you. I shared in the live stream text, I shared a spreadsheet with you. I can do exactly the same thing without even knowing what the astronomical refraction is. So study that spreadsheet and you'll figure it out.
Nice. I'm going to have to study that one too, because I'm not familiar with your method. That's cool that we both independently derived ways that complement each other. It's awesome. Love when that
Yeah,
happens.
we independently derive the same thing with the same values using different methods.
It's
Science.
legendary. All right, lads and ladettes. So yeah, you guys got your homework cut out for you next week. And Jesse, I know we have a do not engage policy, but since this is a new argument, if you have any questions or whatever during the next Celestial Theodolite update, just send me a DM on Discord. As long as it's pertinent to the actual thing, I will answer all your questions so that when we follow up on this Monday, you'll have a better understanding of how to understand what we're putting forward. Does that sound good? Sound fair?
All right. And I often work past when your show goes.
Mhm.
So if I don't get off work, please address the PDF and then let me know that you addressed it, and then I'll go back and catch it on the replay.
Fantastic.
Homework.
All right, lad. Dude, I know if you told me I had to do homework in flat earth, like, fuck, dude, I would have never engaged. now it's too late. All I could do was homework. All right, lads. Thank you all for patiently sitting through that. Hopefully you guys learned a little something or two. We will be back next week to recap and re-examine what we put forward, and hopefully this will be more refined and easily accessible. Like I said, I'll get the link up here shortly, and then people can reference it, figure it out, start dissecting the material, because it's easier to understand when you have all the definitions and everything laid out in a way that you can read it and figure out exactly what it is. So hopefully that helps. We'll see you guys next week, Tuesday, Ether Roundtable number 100, I think. Are we at 100 now? So tune into that. We're gonna be going over something cool, and then Friday will be community Twitter space, and then Sunday, of course, will be Globebusters, where I'll be going over Holton Arp's cosmological debacle, citing mostly from his book Seeing Red.